In this video, we'll take a look inside the nucleus of an atom. We'll learn how the nuclear force and the neutron-proton ratio affect nuclear stability. We'll also calculate the binding energy for an atomic nucleus. This is an atom of helium. There are 2 electrons in the electron cloud, and the nucleus contains 2 protons and 2 neutrons. Like charges repel each other. So why don't the 2 positively charged protons in the helium nucleus repel each other? We know the protons in the nucleus don't repel each other. In fact, the particles in the nucleus are tightly bound. So what holds these particles together? To understand that, we need to zoom in further and take a look at the particles that make up the proton. These particles are called quarks. Quarks are held together into larger particles like the proton and neutron by the strong force. The strong force is one of the 4 fundamental forces of nature. Another fundamental force is gravity, which is responsible for the attraction between 2 objects with masses. The electromagnetic force is responsible for the repulsion between protons. The final fundamental force is the weak force, which is responsible for the process of nuclear decay. As the name suggests, the strong force is the strongest of the fundamental forces over short distances. The strong force is so strong that it results in a force of attraction between the particles in the nucleus. This force is often called the nuclear force. The nuclear force occurs between all pairings of protons and neutrons, protons and neutrons, protons and protons, and neutrons and neutrons. This force is so strong that it's able to overcome the repulsion between the protons and the nucleus, which keeps the nucleus together. But the nuclear force is only this strong under very short distances. At distances of about 1 to 2.5 femtometers, the nuclear force is strong enough to overcome the repulsions between protons. At distances larger than 2.5 femtometers, the nuclear force isn't strong enough to overcome the repulsions. Now we know that protons and neutrons are held together by the nuclear force. This means breaking the nucleus up into protons and neutrons would be working against the nuclear force, which would require energy. This energy is called the binding energy. If we went in the opposite direction and formed an atomic nucleus from protons and neutrons, energy would be released that has the same magnitude as the binding energy. This energy that's released when a nucleus is formed has an interesting impact on the mass of the nucleus. To investigate this, let's continue to use the helium atom as an example. The mass of the helium nucleus has been measured to be 4.00153 unified atomic mass units. We can also calculate the mass of the helium nucleus using the mass of the proton and the mass of the neutron. The helium nucleus has 2 protons and 2 neutrons, which gives a total mass of 4.03188 unified atomic mass units for the calculated mass of the helium nucleus. We can see that the measured mass of the nucleus and the calculated mass of the nucleus are not the same. The calculated mass is larger. In fact, the calculated mass is larger than the mass measured experimentally by 0.03035 unified atomic mass units. This difference in mass is called the mass defect. The mass defect is related to the energy that's released when the nucleus is formed. To understand why, we need to turn to Einstein's famous equation E equals mc squared. This equation tells us that energy and mass are proportional to one another. When energy is released due to the formation of the atomic nucleus, the mass of the nucleus decreases by a proportional amount. We can use this information to calculate the binding energy for helium. The binding energy is the energy required to disassemble the atomic nucleus. It has the same magnitude as the energy released when the nucleus is formed. So if we plug in the mass defect for m in Einstein's equation and solve for E, the quantity of energy we calculate will be the binding energy. Before we plug in any values, we should think about units. The energy in this equation is in units of joules. Joules are defined as units of kilograms times meters squared per second squared. The speed of light has units of meters per second. So the speed of light squared has units of meters squared per second squared. So the mass we plug into this equation should be in units of kilograms. So we need to convert the mass defect from unified atomic mass units into kilograms. 1 unified atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. So we can convert from unified atomic mass units into kilograms if we multiply by this value. This gives us 5.0381 times 10 to the negative 29 for the mass defect in kilograms. Now that we have this value, we can use Einstein's equation to solve for the binding energy. We can plug in the mass defect and the speed of light, which has a value of 3 times 10 to the 8th meters per second. If we perform the calculation, we'll get 4.53429 times 10 to the negative 12 joules. We can leave our answer how it is, but it is common to use units of electron volts or mega electron volts to express tiny quantities of energy involved in atomic processes. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. So we can convert our answer from joules to electron volts if we divide by this value. This gives us 28,303,932 electron volts. There are 1 million electron volts in 1 mega electron volt. We can also write 1 million as 10 raised to the power of 6. So we can convert from electron volts to mega electron volts if we divide by 10 to the 6th. This gives us about 28.3039 mega electron volts, which will round to 28.3. The binding energy of helium is 28.3 mega electron volts. The binding energy is a very large quantity of energy for an atomic process. The ionization energy for hydrogen is only 13.6 electron volts. That means it only takes 13.6 electron volts of energy to remove the electron from the hydrogen atom. The binding energy of helium is about 2 million times larger than the ionization energy of hydrogen. This shows how much stronger the nuclear force is than the electrostatic force. It takes a lot of energy to overcome the attractions between the particles in the nucleus that are caused by the nuclear force. It doesn't take nearly as much energy to overcome the attraction between the positively charged proton and the negatively charged electron that's caused by the electrostatic force. In this video, we've referred quite a bit to helium-4, the isotope of helium with 2 neutrons. There are other isotopes of helium, like helium-2 and helium-5. Helium-4 is the most common stable isotope of helium. Helium-2 and helium-5 are both radioactive. They are unstable and will decay over time. The only difference between these are the number of neutrons, so the number of neutrons must play some role in nuclear stability. If there are more neutrons in the nucleus, that means there will be more attractions caused by the nuclear force to keep the nucleus stable. This explains why helium-2 is unstable. There aren't enough neutrons in the nucleus. Too few neutrons in the nucleus mean there aren't enough attractions to overcome the repulsions between the protons. Helium-5 is unstable because there are too many neutrons in the nucleus. Remember that the nuclear force is very short range. If there are too many neutrons, the nucleus will be too large to be held together by the nuclear force. If we plot the number of neutrons versus the number of protons for all of the stable isotopes, we can start to see some trends in nuclear stability. Lighter elements are stable with a neutron-proton ratio of 1:1. This is what we saw with helium-4, which had 2 neutrons and 2 protons. Carbon-12 also has a 1:1 neutron-proton ratio with 6 protons and 6 neutrons. Nitrogen-14 has a 1:1 neutron-proton ratio, as does oxygen-16. Isotopes of heavy elements tend to be stable with a neutron-proton ratio of 1.5:1. For example, lead-207, one of the stable isotopes of lead, has 125 neutrons and 82 protons. This corresponds to a neutron-proton ratio of 1.52:1. So as we can see, the ratio of neutrons to protons can help us predict nuclear stability. Lighter elements tend to be stable with a neutron-proton ratio of 1:1. Heavier elements need more neutrons to stabilize the nucleus, so heavier elements tend to be stable with a neutron-proton ratio of 1.5:1. This trend occurs because heavier elements have more protons in the nucleus. In order to overcome the repulsions between those protons, there must be more neutrons, providing more attractions from the nuclear force. These stable isotopes are referred to as the band of stability. Any isotopes with a neutron-proton ratio outside of the band of stability will be radioactive. These isotopes are unstable and will decay over time into an isotope that is on the band of stability. We can use the information on this graph to help us predict the kind of nuclear decay an isotope will undergo. For example, this isotope has too many neutrons to be stable. So this isotope will undergo some kind of decay that decreases the number of neutrons. Beta minus decay decreases the number of neutrons, so it's likely that this isotope will undergo beta minus decay to become stable. With that, we've reached the end of what we need to learn about the atomic nucleus. We've learned about the nuclear force and how it holds together the nucleus. We learned how to calculate the binding energy and how to predict nuclear stability using the neutron-proton ratio. Before we conclude this video with the key points, let's work a problem. Which of the following relations is correct? A. To convert an amount of energy from joules to mega-electron volts, we divide it by 1.6 times 10 to the negative 27. B. To convert an amount of energy from joules to mega-electron volts, we divide it by 1.6 times 10 to the negative 13. C. To convert an amount of energy from joules to mega-electron volts, we multiply it by 1.6 times 10 to the negative 27. D. To convert an amount of energy from joules to mega-electron volts, we multiply it by 1.6 times 10 to the negative 13. An electron volt is the amount of energy gained by an electron when it travels through a potential of 1 volt. This unit of energy is commonly used for energy changes in atomic processes. For example, removing the electron from a hydrogen atom requires 13.6 electron volts of energy. Breaking apart the helium nucleus into protons and neutrons requires 28.3 mega-electron volts of energy. Mega-electron volts are the subject of this question. We need to determine the relationship between mega-electron volts and joules. There are 1 million electron volts in a mega-electron volt. We can also express 1 million as 10 to the 6th. So we can convert from mega-electron volts to electron volts if we multiply by 10 raised to the power of 6. 1 electron volt is equivalent to 1.602 times 10 to the negative 19 joules. So we can convert from electron volts to joules if we multiply by this number. The combination of these two conversions gives us 1.602 times 10 to the negative 13 joules, which will round to 1 decimal place to match the answer choices. So 1 mega-electron volt is equal to 1.6 times 10 to the negative 13 joules. We can rule out answer choices A and C as our conversion factor is not 1.6 times 10 to the negative 27. Now we need to know if we should divide or multiply by this number. So if we had some amount of energy in joules and we want to convert it into mega-electron volts, we would divide by our conversion factor. We can see this way that the units of joules cancel, leaving us in the correct units of mega-electron volts. So of the relations in this problem, answer choice B was correct. To convert an amount of energy from joules to mega-electron volts, we divide it by 1.6 times 10 to the negative 13. Now let's wrap this video up with the key points. The nuclear force holds together the protons and neutrons in an atomic nucleus. The binding energy is the energy required to disassemble an atomic nucleus into the unbound protons and neutrons it's composed of. Neutrons stabilize the atomic nucleus. Lighter elements are stable with a neutron-proton ratio of 1 to 1, while heavier elements are stable with a neutron-proton ratio of 1.5 to 1.